Alright guys, so this is second part of water as a food components. Okay, let's start by imagining what we have here is an experiment. You have three container with three different foods. One of the container has pure water, the blue one. The middle one has honey. The one at the beginning here on your left is nuts. So this is just these nuts, this honey and this water will generate the water vapor. So obviously nuts has only one blue dot there, honey has slightly more, but pure water has a lot more. So what we do in the head space here, we measure the vapor pressure of water above the nuts, or vapor pressure of water above the honey, and also the vapor pressure of pure water. Okay, I think the principle is the more and the faster this water vapor move, the higher the pressure. Obviously you can guess that pure water will have higher vapor pressure because of the more water vapor it produces and the more faster it moves. It's going up and down, you cannot escape, because the container is closed. So this is, of course, we have to wait until equilibrium is achieved. Then only you measure the vapor pressure at the head space. So we can just do this calculation. The vapor pressure of nuts, above the nuts, divided by the vapor pressure of pure water, this one, you will get the AW, the water activity. Same thing with the honey, pH divided by P naught equal to AW or honey. So logically, which one between the AW of honey or AW of nuts, which one do you think has a higher value of AW? Well, the clue is in the number of blue dots. Definitely honey has higher AW. Okay, it means a lot in terms of food stability. So another stupid idea somebody has is that why don't we just mix in one same package, we're just going to mix nuts here with honey there. And we learned before that the AW of honey is about 0.6 and nuts about 0.147. So it's not a very smart idea, because the principle is the moisture move from higher here, honey, to lower AW. Yeah, so eventually the AW of the moisture in the nuts is going to increase. That is bad news, because you want to enjoy the crispness of the nuts. That is only possible with low moisture. Now with the increase in moisture, it's no longer be crisp. Okay, second part here, think again. If you're not experienced, you think AW and moisture content is the same. They are not. So I'll show something to give you some kind of shock. Okay, honey has about 18% moisture, nuts has 0.56%, and cookies like Oreo here, it has about 5% moisture. But if you compare the AW, yes, AW of honey is definitely higher than nuts, but surprisingly AW of cookie is the same as honey. You're not shocked? Even though the moisture content of honey is much higher than the cookies. Okay, so do not just think that moisture and AW is the same. So something is going on with honey that make it, even though the moisture is high, but it is able to retain the AW at same AW as the cookies. Cookie is very low moisture, but AW is high. Something so special about honey. Of course, you're not going to learn here, you're going to learn in the future. Okay, so just to compare again, was moisture content and AW. Water is chemically the same, but they can exist in different forms. By definition, moisture is the absolute amount that is just content of water as a component relative to all solid constituents like protein, fat, carbohydrates. So water is just an amount. Versus water activity, AW, this one has to do with the forms, because water can exist in different forms. Water can be free, or water can be chemically bound. I have to show you the other slide first. There are three forms. One is called free water, another called adsorbed water, another is called bound water. Even though many scientists normally they like to compare only free versus bound water, they tend to forget this adsorbed water. Free water is easy. You take orange fruits, you squeeze it, the juice comes out, so that juice is the free water. Or sometimes you see yogurt has this water coming out from it, that is free water. This water is lightly entrapped and can be squeezed from food. The water that you express out can be seen and you can feel it. So this water can act as dispersing agent and also as solvent, and you can remove by drying. Yeah, adsorbed water is when when you take some water, you mix with flour, it become a dough, right? So what happened to the water in the dough? It just got stuck there. It become associated in layers. There is intermolecular hydrogen bonds around the hydrophilic food molecule like polysaccharides and protein. So this bond between proteins and water makes the water not readily squeeze out of the food. You cannot squeeze the dough and expect the water to come out. It's there. So anyway, when we measure water activity, we are measuring the amount of free and adsorbed water in food. Okay. The third types of water called bound water. This is rarely being discussed because, well, we cannot really see the importance in food because it is bound. Meaning it doesn't really display any properties of water, and it will not freeze at 0 degrees C, and it cannot act as solvent, so it doesn't do anything. Anyway, it also cannot support the growth of microorganisms. Free water and adsorbed water can support and promote the growth of microbes, but bound water cannot. Okay, so bound water is inversely related to AW. More bound water, the lower the AW. Okay, so again, water activity is a measure of the amount of free and adsorbed water in food, and it is a dimensionless scale of 0 to 1. Another way to look at it is you just imagine the measurement of AW is measurement of escaping tendency divided by the escaping tendency of pure water. So we've seen the P naughts of pure water divided the P naught of pure water. So whatever is the value of the P naught is still equal to 1. This is the highest possible. Okay, so AW also is a measure of availability of water molecules, whether to enter into microbial, enzymatics, or chemical reactions. So the higher the AW, the more available water molecules to react to get microbes to live. It's like some kind of energy status of the water in the system. Like the names, water activity, how active is the water. Yeah, so this availability determines the shelf life of a food. So fresh meat, 70% moisture, about 0.985. That's very high water activity. That means the water is going to be very active, lots of energy, can cause all kind of trouble in terms of shelf life. But for potato chips, 1.5% moisture, that's low, and water activity is very, very low. Okay, so with this data we can predict stability. We can also decide criteria for specification, meaning you can decide what is the best moisture, what is and water activity that will keep a particular product stable for a long period of time. Okay, this is you can plot this they call this moisture absorption isotherm. You will learn in detail in food preservation, food processing, food engineering. You can plot AW as a function of moisture content. This is the rate of the reaction. Remember, it is log. Therefore, a small change means a big change. Yeah? A small change on the graph means a very large change in reality. Okay, in many cases, microbial growth, most reaction, chemical reaction, except for lipid oxidation, something is very peculiar about lipid oxidation. But most reaction, the rate of most reaction decrease rapidly with decreasing water activity. We are moving from the right to the left. So the lower the water activity, the lower the rate of the reaction. Except for lipid oxidation here at low water activity, lipid oxidation tends to be high. Very strange, huh? You're going to learn why in food chemistry. Okay. This is called the map that we mentioned just now. It's food stability map. You will learn about there are 3 regions: low, intermediate, and high region. A special class of food, intermediate moisture food, is going to be somewhere here. A lot of things, the interconnection and the interaction that going to affect food quality. So the knowledge of AW will help us to control microorganism growth, control moisture migrations. We know how to avoid caking and clumping, especially for low moisture foods, very low moisture foods like powder, 3-in-1 coffee, sugar. Control our chemical reaction rates, and you can predict packaging needs and design, etc. Okay guys, the conclusion is you will learn more in food chemistry, a lot of this, and then you can apply the knowledge in food processing, food engineering, and product development. Okay, so that's all about water as components in food. Next, we're gonna go into more food components like carbohydrates, proteins, and lipids. Okay, so happy learning.